sodium hydroxide, that means that my benzoic acid will react with it. I don't know the formula, but I know the structure because organic chemistry is coming your way, my friends. So this will react with sodium hydroxide to form the conjugate base, right? Because it has to give away its proton to neutralize it. So I end up with something like this. And then sodium doesn't matter. So I end up with something like this, right? So what you want to do is do an addition table. So before addition, the addition, and the after addition. And this sort of, hold on one second. And this will sort of show us the difference in moles, because this is what's changing here, because it's a stoichiometry, sort of a tossback. So before the addition of the base, I have 0.07 moles of benzoic acid, and I have 0.140 moles of the benzenate, sodium benzenate, right? And so usually you might have to calculate the moles if the volume wasn't 1 liter. If it was per se something like 50 milliliters, then I would need to calculate the moles separately. So because it's 1, I know that, molarity, so the 0.07 equals the moles over the liters. So if I multiply 1 liter over, I end up getting moles equals 0.07. Yeah, take into consideration if it's not 1, you're going to have to actually take that seriously. But so we have 0 sodium hydroxide to start. I'll go in red to be concise, and water never matters here. So now I add 100 milliliters of 0.1 molarity NaOH. So I need to find that moles. So 0.1 equals moles over 0.1, because 100 milliliters you have to convert to liters. So you multiply that over to get how many moles you get? 0.01. So I add 0.01 moles to this. And so this reaction will occur, right? So think of sort of like limiting reactants and how the reaction will proceed. I'm not going to lose all of this benzoic acid, because then all of it's required to neutralize sodium hydroxide. It's a 1-to-1, meaning I need 0.01 moles of this acid to neutralize the base that I add. So this will take away 0.01 mole here. And so when it takes away, so this acid does its thing and donates here, I'm left with adding 0.01 mole of the conjugate base, right? So when I do that, I end up with 0.06 moles, 0 moles here because this is completely neutralized, and then I end up with 0.15 moles of that conjugate base. And so now it wants the pH, and now I'm just going to use Henderson-Hasselbalch, because remember, it's a buffer system, and that's when I use Henderson-Hasselbalch. So pH equals negative log of 6.5 times 10 to the negative 5 plus the log of 0.15 over 0.06. So when you do that, you should get something like, 1 second, I have it written down. So you should get like 4.58. So something important to note about buffers, which conceptually you could be tested on, is one, it's going to be weak acid and a weak base. So, and they have to be conjugates, right? That should go without saying at this point. So HCl and NaOH are not a buffer solution because those are both strong. I can't have a strong acid and a weak base. That's not a buffer. A buffer resists pH change. Oops, sorry. It's going to resist pH change. And beyond that, if I want to look at the efficiency of a buffer, they're going to be more equal. So concentration of OH. No, I don't want to say OH. I'll say concentration of some acid. I just put HA is equal to the concentration of the conjugate base. So buffers are more efficient when their concentrations are more equal, and they're also more efficient when they have high concentrations. So a high concentration will allow it to better withstand pH change due to, adding 100 milliliters of sodium hydroxide. So now the next problem. Using the same information, calculate the pH after the addition of 100 milliliters of NaOH. So it's still the same concentration. So now it's 0.015. So for this, what you need to do is the same thing as before. You would write out your before addition, your addition, and then your after addition tables. Before addition, addition, after addition. I'm just going to say HA. I'm going to say an OH. Something like that, because I don't want to write all this out from up top. So before addition, I have 0.07. Here I have 0. Here I have 0.14. And water never matters, but that's okay. We still keep writing it down. So I add 0.015. I subtract 0.015. I add 0.015. So I end up with 0.155. I end up with 0 because that's completely neutralized. And I end up with 0.055. So now I'm just going to do the same thing as previously. I do my pH equals my negative log of 6.5 times 10 to the negative 5, which I did in my calculator previously, so it's already written down, and so should you, plus the log of 0.155 over the log of 0.055. So when you do that, you should get, or I ended up getting 4.58. No, 4.64. Sorry, there's a bunch going on here. 4.64. All right. So this next problem. Consider the titration of 50 milliliters of 0.1 molarity benzoic acid. Oh, there's the formula. Crazy. And with 0.1 molarity KOH, calculate the pH after the addition of 25 milliliters of potassium hydroxide. Sorry, 1 second. All right, so this doesn't have any sodium benzenate to start, or like, oops, sorry, something dropped. So what I want to do is still do my addition tables. I'm just going to put acid, the titrate, and then the base. Sorry, I'm sort of writing these all in different ways. I'll just write them concisely. So HA, there's that OH, A minus. So before addition, I end up having, remember, now this is where I have to calculate the actual number of moles. So I have to multiply. I have to do 0.1 equals moles over 0.05, and you should get 0.005. Don't be scared by small numbers. It's okay. I have 0 here, and I have 0 here. So I add 25 milliliters of 0.1 molarity KOH. So you have to do the same thing. You have to do 0.1 equals moles over 0.025. Multiply that over, and you get 0.0025. So I add 0.0025. So this benzoic acid will completely neutralize it. So in doing so, I'm left with 0.0025 of that acid left, but because it reacts and donates its hydrogen to neutralize, I end with 0.0025 of the conjugate base, which is benzenate, right? So something important to note here is these concentrations are equal. I have an equal amount of the conjugate acid and an equal amount of the conjugate base, meaning that this is the equivalence point. Concentration of the acids and the base are equal. And at this equivalence point, pH will be equal to pKa, meaning my pH will equal negative log of 6.5 times 10 to the negative 5, which I think was like 4.18. So if you see that after addition they're equal, then the pH is equal to pKa. Fun stuff. All right, which of the following is a buffer? Now remember what I said about a buffer. A buffer has to have a weak acid and a weak base, and they have to be conjugates. So A has nitric acid and nitrate. Well, nitrate is strong, and this doesn't even act as a base because it's neutral, so I can automatically get that out of there. These may both have chlorides in them, and they do, but NaCl is a salt, and it's neutral, and this is a strong acid. X, goodbye. Same rationale as before, as like in A, this is strong, so this is neutral, so incorrect. And I know because this isn't on my list, this is weak, So that means that this is weak. It means that it is a buffer system. All right. Which of the following, when mixed in equal molar amounts with its conjugate acid or base, will produce a buffer with a pH of 8.7? So it's important in science, or in science, sort of for scientists to be able to create these buffer systems because like that operate at certain pHs, meaning they'll sort of stay near this pH and they won't deviate very far, right? So we have like a bicarbonate shuttle in our blood that keeps our pH near 7.4-ish. So if they're in equal molar amounts, I just want to find the pKa that is closest to my desired pH. Because remember, as before, when I have something like, if I have pKa plus like log, let's say their concentrations are the same, so I end up with like 1/1, that log of 1/1 or log base of 1 is 0, right? So that's why I know that my pH equals pKa, is because of when I plug that into my calculator, I get 0. So now you just want to take the negative logs of all these Ka. So I'm going to take the negative log here. I want to take negative log here. And when I plug into my calculator, the closest I get, sorry, I get 8.67 here, and automatically I'd be like, oh yeah, it's probably A, but you still want to check your other answers. So 4.72 here and 3.75 here. So yeah, A would be my best buffer to maintain a pH of around 8.7. All right, so consider the titration of 50 milliliters of 0.2 molarity hydroiodic acid with 0.1 molarity sodium hydroxide. Calculate the pH at the initial point. So this is totally just a little like trying to fool you. There's no crazy tricks here. The initial point is the point at which there's no titrant. That means that I only have HI in the flask. Sorry, I can't write. Okay, you get the point. There's only HI in the flask, meaning that if I want that pH, I just solve for the pH of a strong acid. And so for solving for the pH of a strong acid, that's just the negative log of the concentration. And we've already talked about that. So it's just negative log of 0.2. And so when I do that, you get 0.698. So really, you shouldn't be scared of buffers. It's just you just have to take into consideration these before additions and after additions, etc. So often what you could get is a case where, let's say I have, I don't know, I titrate something. Let's say I have like HA, OH, and then A minus, and then H2O. That's just me writing it out very basic. I could have something like this where I end up using up all of my acid to the point where I have like leftover hydroxide. If you have leftover hydroxide, like this will react all the way, so this will end up being something like 0, but I could have like, let's say like 0.02 moles of hydroxide left. And it would want you to find the pH. Well, what you would need to do in a case like that is look at the volume. If the volume is 1 liter, then I would do like 0.02 divided by 1 liter to get my molarity. And I would take that molarity and do negative log of, I don't know, it would be 0.02 at this point to get my pH. Or if it says, like, if the question phrases it as like, oh, I add 25 milliliters of a 0.1